Okay. So I'm going to come back to this question that I have about why does the water not get super clean when you add when you have a really dirty suspension to start with. I'll just highlight here that the mechanism that we think, and we're pretty sure about this, is dominant in causing collisions between particles is viscous shear. And indeed, that's precisely what we're using when we design a flocculator. Is we're designing it so that we get fluid deformation that causes particles to collide with each other. So it's the one in green, that's actually the one that we think is the dominant mechanism. We add a coagulant, and we add enough coagulant so that there's coagulant at the point of contact. So wherever two pieces of clay hit, if there's coagulant there, that will be a sticky point and they'll have a chance of actually attaching. So they will attach if and only if there is clean coagulant at that point of contact. And we can use that to actually figure out probabilities of a successful collision. And that means that unlike conventional theory about flocculation, which, by the way, what I am teaching you in this class is very, very different from the conventional understanding of flocculation. And I'm not actually going into the conventional theory because it is so clearly wrong. But it means that if you run into it, when you go into industry, there will be a lot of surprise because this new understanding of flocculation is still just beginning to get traction out there in the broader world. So one of the things that we predict is that if you add a tiny bit of coagulant, you'll begin to put a few coagulant nanoparticles on the clay particles, and there will be at least a little bit of a chance that when these two clay particles, or when two clay particles collide, that there will be a sticky point there. And so even with a little bit of coagulant, you'll start to see a little bit of improvement in removing particles. And as you increase the coagulant dose, you'll be coating your clay more thoroughly. The probability of attachment will improve and flocculation will happen faster. Conventional would predict that you will get no effect when you add coagulant initially. And I'm going to skip this slide because it's just too much to look at, but it's there if you want to look at the comparison of what was previously understood and what we are now hypothesizing. But now we come back to what you have been thinking about as far as if you have lots of small particles and some big particles, some big flocks, will those big flocks end up acting like attractors that end up taking those little particles out of suspension and moving them into the big flocks? And this is a really key insight, that we are hypothesizing that primary particles, like little clay particles, little pathogens, cannot collide with a big flock when it's in a shear environment. And that's because of this. In a shear environment, the flocks are rotating. So first of all, do you understand, do you see why the big flock is rotating? It's because in a shear environment, the velocity is high up here, or from the perspective of if you are the particle in a shear environment, if you look up, the velocity is high in one direction, and if you look down, it's high in the other direction. And so you're experiencing this. And so you're going to spin in the middle. Do you see that? In a shear environment, if you're a particle in a shear environment, you're going to spin. Once you buy that, then the next part is viscosity is super important here. And so think about you're a little flock and you're rotating in honey. And the honey is deforming, and that's what's causing you to spin. And what's going to happen is you are going to move a bunch of honey around with you. Can you kind of imagine that? So the particle, the flock, is going to be dragging fluid around with it. And so there's going to be a boundary layer, a layer of fluid that just is spinning, not quite as fast as the particle itself, but the flock, but is spinning around with the flock. And so what that means is that the streamline for this poor little clay particle that would love to attach to this big flock, the streamline that it's on doesn't actually get close to the flock because there's all this fluid next to the flock that is spinning around with the flock. And so the closest streamline that's going past the flock is actually far away from the flock itself. Is that cool? Because of how viscous it is, the streamlines don't actually get close to the flock. So this particle that thought it was heading straight towards the flock actually deflects around it, because the fluid that is being carried around by the flock itself is acting as if it were part of the flock. So that means that in order for a particle to actually collide with another particle, it has to be big enough so that its radius can extend through the boundary layer that it and the other particle are creating. So the conclusion from this is only similar sized particles can extend through each other's viscous boundary layer. You have to be big to interact with another big particle. So here's two big particles. And now look what happens. Now the streamline that is going through the center of the particle on the left, the streamline that would be going through the center of the particle on the left does deflect up as it goes past the second particle, but not so much that the second particle isn't able to reach through the boundary layer, because the first particle has a really large radius. So here we go. So it's going to deflect, it's going to move up, but it actually is able to penetrate through the boundary layer because its center is following the streamline, and it's able to push through the fluid that's in that boundary layer. So given this notion that maybe only similar sized particles can actually attach to each other, can actually collide with each other, then this is a very simplistic perspective on what happens inside a flocculator. There's some random motion of particles. There's the fluid is being sheared in many different directions. And then there's sadness, because there's no one for this last little particle to collide with. Aren't you all sad now? Like, this last particle would love to collide with someone, but there's no one else out there. And this is why at the end of flocculation, it doesn't matter if you start at 500 NTU or at 5 NTU or at 1 NTU. By the time you get to the end of flocculation, the number of solo particles that have not combined with any other particles ends up being very similar. It's always about the same. Because it's the flocculation process is not catalyzed by the big flocks. The big flocks don't help remove the solo particles at all. Oof. Any questions about that? I don't know. It's like, you could tell all kinds of stories about this. Maybe you can tell a story to your friends about how there are these cliques that form and they don't let anyone else in, right? Okay, and then if you're pondering, you might have the question about, well, how do coagulant nanoparticles ever find their way onto the clay? Because I just tried to argue with you and tell you that little particles can't attach to big particles, right? So if you believe what Monroe says, then the next thing is, well, coagulant nanoparticles are much, much tinier than clay particles. So then how does the first part of coagulation ever work? And unfortunately, I think I answered the question on this slide. It's because there's something else that kicks in for nanoparticles, and that's molecular diffusion. So molecular diffusion provides another transport mechanism that allows the coagulant nanoparticles to just zip around randomly and slowly penetrate through the viscous boundary layer around the clay particle and actually get in. So I contend that if you had some magic way of turning off molecular diffusion, that we would not be able to get the coagulant to actually attach to the clay particles, but diffusion does that for us. Okay. Woof, we almost proved that flocculation doesn't work there, but we got through. And I'm having a lot of fun these days. This course is making me like rethink everything again. And because I hadn't taught it for a couple of years, a whole lot has changed over the last couple of years. And I feel like we've been working on this thing for a very long time of, can we begin to develop equations that describe the entire water treatment process so that we could begin to figure out how to optimize the process? Because otherwise we're just doing things randomly, which we've been doing random things for more than 100 years, trying to figure out how to get good designs for water treatment plants. But it was never on the basis of a solid understanding of what actually is happening. So we're making a little bit of progress. We are by no means have we figured this all out, but we're making little steps forward. And in each of our paths or each of our steps, we're trying to figure out what's happening to these little particles that didn't get flocculated and what's controlling what their concentration is, because they're the problem. They're these little particles that end up sneaking the whole way through. They don't get flocculated, they escape the sedimentation tank. Some of them sneak through the filter, and those are the particles that end up at the very end of the process, giving you a little bit of turbidity in your treated water. And that's what we would like to figure out how to do better. So there's still a lot of work to be done. 3 ideas. So here's one. In laminar flow, where it's viscous dominated, only similar sized particles can collide. So there's that. In flock blankets, and we'll talk about these eventually, in flock blankets, we have a situation where we have water flowing up through a suspension of flocks that are just kind of hanging out because they're settling down as the water is going up. And in flock blankets, it is possible for particles to collide, for small particles to collide with big particles. But it's a very interesting case. In the flock blanket, there's much less shear, and so the flocks aren't rotating and creating this boundary layer around themselves. But instead, we just have like this big web flock that's falling slowly in the water, or the water is traveling up through and around the flock. And the key here is some of the water flows right through the flock. So the flock is actually very porous. So water is flowing right through the flock, and because it's not spinning and creating a boundary layer of fluid around it, it's possible for a little particle to actually go right into the flock. And so that's what we think is happening inside the flock blanket. Oh, we missed one. Okay, and then in the filter, we hypothesize that in sand filters, the way they work is they're able to capture big flocks because the pores of the filter aren't that big, and big flocks literally just get caught in those pores. And then little clay particles actually travel through those flocks. So the flocks that are caught by the filter are the actual filter that captures little clay particles. And this is that same problem of the boundary layer. The boundary layer on the sand grains is preventing clay particles from ever getting close to the sand grain. But these little porous flocks that have water flowing through them, these little porous flocks that are stuck inside the pores of the filter, clay particles are able to go right through those, or water is able to go right through those, and some of the clay particles hit other clay particles that are in that flock and hence get captured.